Okay, hello everyone. Welcome to today's webinar on Warpage and Strain Characterization using TDM. My name's Aram Sarkisian from EAG Labs. We're a Eurofins company. Before we get started here, and I see a lot of people are still entering the room, but I'm going to go through a few housekeeping rules, and for those that come later, you'll just miss these. But you are all as attendees muted, so you won't be able to speak during the presentation. However, we know people have questions, and so we invite you to type those questions into the questions box in the webinar screen. There's a questions box. Please put them there, not in the chat box, but in the Q&A box. And we're going to answer them at the end of the presentation. And the other thing we'd like is once we finish the presentation, we'll be sending out a survey. It should pop up on your screen, and we really greatly appreciate you filling out that survey. It really helps us prepare for future webinars and information. So those are the few housekeeping rules. With that, I'm going to advance to, there we are. Okay, so today you've got a couple of people speaking, me very, very shortly, and then I'll turn it over to Pierre. But I'm Aram Sarkisian. I'm the general manager of our engineering sciences group here at EAG. I've got a lot of years in this laboratory space, managing both the operations and commercial activity. And joining us today, I'm excited to have Pierre-Louis Toussaint with us today. He is with Incidix. He is the TDM technology expert there. He has been with Incidix since 2013, both in applications and engineering roles, and really involved in the fundamental journey of Incidix as a company. So he's got a background in mechanical engineering as well as a master's in bioengineering. And so we'll hear from him today. Very, very excited to have him with us. A little bit about the webinar today. We're going to go through the technology. Pierre's going to walk us through that shortly after I do a little brief intro on EAG. And then we'll get really into case studies. And I think that's where the exciting stuff is, where you can see how to put this technology to work. Just a couple of quick slides on EAG. You can see our footprint. We're a worldwide organization. I'm not going to run through all of these. We have laboratories all over the world. And really, we're a services organization with 4,000 plus clients, 50 countries served, and 600 plus people. So lots of horsepower in our lab, and welcome you guys to just check that out on our website. As far as our engineering sciences division goes, what we do in our company is really a lot of things intended to provide an integrated set of services for IC and microelectronic folks to bring that innovation to market. And so the domain expertise is in things like test, reliability, circuit edit, failure analysis, and all of that under one roof, so to speak, to provide an ecosystem of activity to help our customers. And so really today is the TDM technology is relatively new for EAG. It's something we have in-house. We're very excited to feature, as it really helps us bridge a lot of these different things, both in terms of both failure analysis and reliability, and sort of those initial innovation and product design. So pretty exciting, and of course, we're going to hear a lot about it. And with that, I'm going to turn it over to Pierre. And Pierre, please lead us through the TDM technology and what it can do for us.
Okay, thank you very much, Aram. So yeah, today's webinar is I will present the TDM technology and see some case studies where the technology can bring some useful information regarding IC components. So what is TDM? TDM stands for Topography and Deformation Measurement System. And TDM is a patented range of instruments for warpage analysis. So will measure the topography of any component under a temperature profile. It uses a fringe projection technology which is called prediction moire technology, which allow non-contact full field acquisition of 3D topography with a resolution as low as 1 micron. The TDM acquires a full absolute 3D cartography of devices with dimensions up to 400 by 400 millimeters square. Simultaneously, its powerful heating and cooling capabilities allow for virtualize any temperature profile on the sample under test. The integrated software package provides tools for representation of the result as 3D plot, vector diagram, isometric views, and 2D profiles following user-defined profiles. Like here, okay. The typical result for well-studied technology is that we can see the shape of IC component package, for instance, at different temperatures. So here we can see through this temperature line that at about 30 degrees C, the package we need to analyze has a concave shape. So we have the part in dark blue, which is in lower position, than the part in red and white here. And we can see at the measurement point in red here. And little by little, when the temperature rises, we see the shape change from concave shape to convex shape. Below this shape, we can see the warpage value here, which is a maximum versus minimum distance within the zone of interest, the package. So the type of result we can provide is this kind of shapes for any type of component. And it is valuable because it can give information about the internal stress on the component, or the quality of the connection if we are measuring like if we're considering the connection over like solder bore or something like that, and so on. The two main applications for warpage analysis are reflow simulation and reliability testing. So during reflow simulation, the most like typical temperature profile is room temperature up to 260 degrees C, and then come back to room temperature. The point is to simulate the reflow of the package through one cycle or two cycles sometimes, and we check the shape change and the warpage behavior during this profile. For reliability testing, we go through many cycles. Most of the time it's from -40 to 100 or 150 degrees C, and we check if the behavior of the sample is the same during the first cycle, the second cycle, the third cycle, and so on. TDM technology allow to measure the topography of sample using phase shifting prediction moire. This measurement process requires to use a digital projector to send some some structural light on the surface on the zone of interest. So we can see here some stripes, and the camera is checking those stripes. The stripes are moving, and then the distance, I would say, between the black and white parts of the stripes depend on the topography of the surface to measure. So this 3D sensor allows to get a high resolution. The data is scalable, meaning that we have everything not in pixel size, but in millimeters or microns. And it can measure the surface discontinuities with high amplitude range. In the meantime, the sample is being heated up from top and bottom using double-side infrared heaters, which allow good XYZ homogeneity and fast temperature ramps. This is a short video which I have a little lag in my computer. This is some video which show how the measurements are being processed. So we can see some stripes moving on the sample. And once again, the main probe of the 3D sensor are the video projector here and the camera here. We can see that there are a lot of like 5 different zooms which can be connected to the camera and the projector, which allow to get different size of zone of interest. I will go more in detail later. So TDM can be used in many steps of product design, such as R&D, process control, design of the manufacturing, quality control, failure analysis. We have been developing like the Compact 3 system, the latest system, after investigating the market and understanding the new needs for warpage measurement. We have more and more lead-free solders with a higher density and smaller bolts, thinner component and PCB, larger BGA type devices, and higher heating dissipation. So in order to analyze all this new material or all this new IC, I would say, we need to have we need to improve some part of the tool, and the Compact 3 system allowed to get like a good resolution, sub-micron resolution, with high homogeneity for the infrared heaters. We have the capability to heat up with convective oven as well as the infrared heaters. We have a temperature range from -60 to 400 degrees C, fast heating and cooling ramp. The sample can be from 0.5 millimeter squared up to 300 by 300 millimeter square. And one breakthrough is a multi-scale analysis. I will go more in detail here. So, as I said before, we can adapt different zoom extension on the camera and the projector. And according to the zoom extension, we adjust different FOV, standing for field of views, which is the area where we take the measurement. On a field of view 10, we have area which is about 10 by 12 millimeter, and we have a pixel density of 40,000 pixels per millimeter square, which means that we can be very precise. You can see very precisely the structure of like the very local structure of components. And the larger the field of view is, of course, the lower the pixel size is, and we have to find good between the size, the global size of the field of view, and the precision of the size of the pixel itself. So, for instance, if you measure a strip, and if you just zoom on a single unit, of course, measuring this single unit with a field of view 10 and field of view 300 will show very different quality. On the field of view 10, we have 5 megapixels, which are covering this small area. On the field of view 300, we just have 5,000 pixels. Although the Z resolution is almost the same with all field of views, the XY pixel size is important information to get good understanding of the structure and shape of the samples. So with the system, we can use the scanning mode, which means that we can move the 3D sensor at different positions during the sample profile, which allow through one profile, for instance, to measure the whole strip here, and then at the next temperature or at the same temperature, measure with a different field of view some local areas. We have just a small video which gives some overview of the system to let you have a better understanding of the way the system is working and the type of data which can be taken with a compact system. So we can see here that the camera and the projector are moving all together, and it's not easy to see right now, but yeah, now we can see that the stripes are moving like this, and it's allowed to take data at selected area and selected zoom extension. So for instance, here, if you measure with a field of view of 30, so it's about like 30 by 37 millimeters, we can measure the top part of the ship. So this is here the image in grayscale, and below the 3D image you can get. Something here, if you want to check the discontinuity, like the edge, we can measure the edge at the post-processing. And it is also possible to change the field of view to have a wider zoom extension and change the position at the same time. So as a raw data, we get all the information with no limitation over the surface discontinuities, and then we use the post-processing software to get the information we need to get. So here it was just the edge of the board. So some application for the TDM technology. One we use a lot is solder ball analysis. Point here is to measure the ball coplanarity at different temperatures. So we have the possibilities to automatically position the balls. To detect the ball maximum values on a BGA, and then get this kind of view at all temperatures. Reliability testing, so I mentioned that before. The point is to measure during many cycles, something like -40 or 50 degrees C up to 150 degrees C. Here it's an IGBT model, and check if the behavior is the same during all the profiles. We also have a 3D CT capability. So the 3D CT can be taken at the same time as Warpage itself. The 3D CT is working as like 2D CT and using DIC algorithm, DIC digital image correlation, combine two 3D data. So the principle is that we need to paint the sample to measure to have some random pattern on top of the sample to measure to allow like shape tracking using DIC. And then from the grayscale image, the software will track the shape extension, which will give the 2D CT, and combine with the warpage information, we can get the 3D CT. So for instance, here we have like a component with a die at the center, and we can clearly identify like from room temperature. If you go to -40 degrees C, we can see that the part, like the arrows, are going to the center, so the sample is like getting constrained. That the die itself, the arrow are not showing any direction, because compared to the substrate, the die does not move a lot. We can see that in the color scale here. So it's red, it's close to 0, and the other part here, it's in green and yellow, it's close to 1000 ppm for the strain. And if you go to 260 degrees C, we have the opposite behavior. So the substrate is going to the outside part, and the die is not moving. So you can have different measurement like this. So just quickly, I show some other application examples. So we can measure sockets, IC component, copper pad module, strip units, all these components through always a profile, and we get the information at all temperatures. Wafer level packaging, power modules, and that is all for the introduction with student technology. So now I will show 4 case studies. So case number 1, it's how to characterize BGA with balls. So package characterization. When we measure like a BGA package, we need to identify the risk during package soldering. So one question that might rise is the soldering correct or not here? And how can we make sure that the connection is good, or that there is no internal stress on the solder bore area, which will lead the component to disconnect or to break after some use. So in order to answer to all these questions, I run an analysis with like 6 similar packages, 4 showing the bottom side to the camera and 2 showing the top side to the camera. And the point is to measure the ball and substrate shape at different temperatures during the reflow process, and compare also the top side shape. So one profile was like this, so room temperature, then measurement every 50 degrees C, so 50, 100, 150 degrees C, 180, 220, 250 to 60, and then come back to room temperature. We measure all the sample with the same field of view, the field of view of 30 altogether. So we have a pixel size of 16 micron and accuracy in Z of around 1 micron. So from the raw data, we can get on the sample image like this. So we can clearly identify the ball, the substrate, and like the higher line here. In the post-processing, it's possible to extract the ball coplanarity and the substrate coplanarity. So if this graph is just profile extraction from this line here, so we can see the ball here and the substrate here. This is just to explain how the process is done. The system automatically detects the maximum of the balls, the area, and then either take the maximum and recreate a 3D image based on the maximum of each ball, or use the ball map as a mask map to mask the ball area, and then we get the substrate. And then we could measure at all temperatures the solder ball and the substrate shape. So we can see that at room temperature we have a smile face. And then when temperature rises, it's getting like flat. And when the temperature is going back to close to room temperature, we recover this smile face. We can see this phenomenon on the ball area and on the substrate area. So we can see that for all four. And if we see the graph here, so we have a sign like the minus sign is for concave smile face and the plus sign is for convex cry face. So we can see that the ball area has a little bit lower warpage openarity than the substrate because the area of measurement was not the same. Substrate larger area of measurement. And the concavity is changing around 150 degrees C, something like that. So below it's concave, above it's convex. And the value is very low at high temperature. Measure then the opposite, the top side, we have the opposite shape. So we have cry face at room temperature, flat at high temperature, and we recover cry face at room temperature. And we can have the kind of opposite graph if we observe the top surface. So to answer to the initial question, what we can say is that during the heating, the sample is getting like has a much more flat shape, which means that when the ball are soldered, the surface of the ball might be very flat and very close to the surface of the PCB. So the connection should be good. However, when you come back to room temperature, we see that the sample tend to recover its initial shape, which means that we can have internal stress on the connection when the system is like regularly used, which means also that if the PCB is being like heated and cooled down many times, we can create some increase that stress inside, and this could be some quality issue. Case study number 2 is strip characterization. So here, when we measure a strip, we like in information which can be interesting is to get the global strip shape and some local unit behavior at the same time. So it is possible to to see those both information at the same time during same thermal profile. On the first step, we measured the strip at room temperature using field of view 300 versus field of view 10. And then we measure during thermal profile using field of view 300 versus field of view 30. So you can see here, this is a raw data from the after measurement with the field of view 300. So then this kind of part here are the thermocouples. So if we have a look on the field of view 300, we can see the global shape of the strip. So you can still partly see the structure here. After post-processing, we can get the shape for the warpage measurement. We have warpage around 1,200 microns. And if we have a look on local strip, we can see that on each strip there are some small snowball attached. So on the raw data, we can clearly see that structure here. In order to get the shape on the local unit, we need to zoom on the area to remove these connections and then extract the substrate shape. So this could be done at different zones. For instance, here zone 1, you have a very shape with two profiles here, two diagonals. Zone 4, so you have a quite different shape here. Zone 10, zone 13. So you can see that the shape is quite different according to the area we are watching. So after measuring the strip with a field of view 10 at room temperature, we could take a thermal profile and measure if that room temperature 30 degrees C, 150 degrees C, and 250 degrees C, and back at 30 degrees C. All the different locations with a field of view of 30, and at the other point measure the global strip shape with a field of view 300. Doing so, it's possible to get one profile information like this. So this is absolute warpage. Absolute is because like it's the real warpage and the real shape created by on the strip at different temperatures here. So we can see that we have like some area here which is getting higher, and then during the cooling we have the center part here which is going in higher position. Sometimes it can be useful to remove the initial shape to see the trend as regard to room temperature, which is a relative warpage. So if we watch the relative warpage, it shows, it emphasizes the phenomenon. So you can see that there are some bumps here, which means that this part is getting warped as regard to room temperature shape. And during the cooling, we have the whole part here, which is getting in higher position as regard to room temperature shape. Of the warpage, absolute or relative warpage, and at the same time we could measure the different areas. So for example, for 330, we could after getting the data like cut the part and analyze the 16 different chips independent to each other. So we got here the absolute warpage, relative warpage. Absolute warpage shows the real shape. Relative warpage shows the trend during the thermal profile. There are less temperature point because it's just a room temperature, 150, 260, then back to room temperature. Measure it for the different zones. 11. And finally, we have a conclusion. We could measure the strip and the global shape and the local unit at the same time. And we also observed that the local unit deformation depend on the location. And especially if we have a look, if we have a comparison with the field of view 300 and field of view of 10, we can see that the shape observed with field of view 10 resulted, what was the resultant from the global shape of the strip. Case study number 3, it's analysis of a composite material. So for this case, like S company has developed 2 composite materials for aeronautical application. They need to compare warpage and CT characteristic for both materials. Is possible to characterize mechanical properties under thermal stress, and it is possible to correlate this result with other technologies, for instance, X-rays. So same story as before. Sample has been prepared. You can see here some black pattern because the sample has been prepared for warpage and CT characterization. And during these two profiles, we could see the shapes, the room temperature. We have like almost, let's say flat because it's still 0.4 millimeters, but compared to the next image, it is almost flat. Then at 150 degrees C, we have a huge smile face. Then back to 30 degrees C, we have a quite different shape than before. It's a cry face here. Then back to 150, we recover this smile face and cry face at 30 degrees C. If we check the CTE, so we measured this zone here, and we could get, we can see with these arrows, the extension on the range of 25, 100 degrees C. 25 being at the reference and 100 degrees C at the measurement point. So the CT between these 2 points is being measured here, and 120, 150. So its reference is 120 degrees C, and the CT is measured at 150 degrees C. We compare the shapes, we compare the pattern, I would say, which allowed to get the extension. So we could see that the CT, global CT, is very big for this composite material. So it's around like 90 ppm per Kelvin in the range 25, 100, and 120 degrees C. And at the highest temperature, 120 to 150, we have global CT of 136 ppm per Kelvin. Then we measure the material number 2. So the first thing you could see is that for the warpage measurement, we can clearly identify a direction. Before it was an isotropical behavior. This time we have clearly difference between the X and Y axis. If I consider the X axis, so that the one that I draw with the mouse. And we still have a smile face at 150 degrees C, cry face at 30, smile face at 150, cry face at 30 degrees C. What is interesting is the CT also. The value is much lower than for the other sample, but we can see here that the arrows are like getting bigger in the y-axis and in the x-axis. So this vector suggests that the CT in x and y are different. The CT as one value is an average extension on the sample, whatever the direction is. So from this data, we can get that the global value for the CT might not be meaningful, and we divide the CT into the CT in X direction and Y direction, and then we could clearly identify two different trends. The CT in X has a comparatively low value, and the CT in Y has a high value. So it means that there is a much bigger extension through the y-axis than through the x-axis. In order to better understand this phenomenon, we measure with X-rays. We analyze through X tomography the glass fibers, and we could see that the sample had the glass fibers oriented through the x-axis. So this fiber orientation created this CT mismatch between X and Y. So I will go to the last case study. It's a socket quality comparison. So the company wants to compare the quality of various socket suppliers. What I want to get is the socket which will have the smallest deformation through the thermal profile to make sure that the connections are good at the end. So Same thing, we could measure these sockets through room temperature 260 thermal profile, and we measure the socket like connection here, and from that we use some filling algorithm to get the global shape to have like a better like visuals. So from the supplier 1 showed that we had a warpage at room temperature around 60 micron. Then at 50 to 60 degrees C, the warpage increased to 120 micron, and back at room temperature, the warpage is quite different according to the samples, but it's around 100 micron. Supplier number 2, we have a quite different behavior. The warpage at room temperature is higher, 80 degrees C. We can clearly see the shape here, which is a clearly concave shape. Then at 260 degrees C, we have warpage of about 100 degrees C. We can see we have a convex shape here, and then back at room temperature, we recovered the initial shape and with bigger warpage, around 140 microns. Yes, 3. So same type of shape, but the value is much bigger for 260 degrees C. And sample 4, the type number 4 showed a value which is much lower as regard to the other components. So this supplier 4 was chosen. I hope I interested you with these examples. Thank you very much for your attention, and I will give back the word to Aram to the next part of the presentation. Thank you.
Yeah. Hey, thank you very much, Pierre. That was a great presentation. I think we're going to move to some Q&A. Really appreciate it. I think one of the things, one of the takeaways from just looking at the case studies is the range of different, sample types and let's say assemblies that you can do with this tool and with this technology.